Okay, well, happy Wednesday, happy week 9 Wednesday. Our final exam is going to be 10th week Friday. I am still working on writing the exam and trying to figure out exactly how best to do this. And so give me a few days to figure that out. And I would say by Monday, I'll have a pretty good idea of what the final exam will look like, and I'll give you some more information regarding how best to prepare for that and whatnot. So I'll talk more about the final, I would say, on Monday. So today we will take a look at Bootstrap. Okay. On Monday earlier this week, we looked at the randomization test. Today's topic, the Bootstrap, is similar, but different enough. So just going back and just reviewing, sampling distributions is kind of the foundational idea that we use for inference. Okay, the sampling distribution of a statistic is basically the distribution of all possible values of a sample statistic from all possible random values, possible random samples drawn from the population. Okay, and the idea is that when we look at the sampling distribution, we get a sense of how much the particular sample statistic can vary from one sample to another. And if we have data, we can compare the sample statistic from our observed sample with the sampling distribution if the null hypothesis were true. And based on that, we can then kind of figure out a p-value and then perform statistical inference in that way. So let's keep going here. And in your intro stats class, your sampling distribution is basically based on the central limit theorem. So the idea from the central limit theorem is that your sampling distribution is going to follow the normal distribution, okay, with this mean and the standard deviation. All right, but this only applies if your sample statistic is something like the mean or the sum of a sample. Okay, so the sum of the sample or the mean of a sample, which is basically the sum divided by n, is going to follow the normal distribution. The central limit theorem works there. But if you're talking about a different statistic, such as the standard deviation or the variance or the maximum value or something like that, those things are not going to follow the normal distribution, and you can't use the central limit theorem. And you have to kind of recall basically other mathematical distributions, other probability distributions that are going to work, right? And so, for statistics other than the mean, we need to rely on our mathematical knowledge of probability distributions. But the nice thing is that even if we don't remember which distributions to use, we can use simulation to approximate the sampling distribution. And, all of these simulations that we're going to do require that we make assumptions about the population. Okay, and that's going to apply throughout all of statistics, is that you have to make assumptions to kind of fill in your gaps of knowledge, because the idea is that we don't have direct access to the population. We only have access to a sample. And so to kind of go from the sample to the population, we've got to make certain assumptions. And so we might make assumptions about the population's shape or its distributional form. We might make assumptions about the mean or the standard deviation of the population, or what kind of values appear in the population. But once you've established your assumptions, then you can simulate the sampling distribution. And we're going to do that by just kind of repeatedly drawing samples of a given size and recording whatever sample statistic we're interested for each sample. So let's just take a look for at how this works. And this is we're first going to look at the parametric bootstrap. Okay. And so kind of the process where we simulate the sampling distribution by making parametric assumptions about the population is known as parametric bootstrap. So parametric assumptions are things where you are assuming the population follows some exact distributional form, and that the the parameters of the population have certain properties. So you're going to assume that the mean, which is a parameter, has this value, or the standard deviation, which is another parameter, has this value, or maybe it's not the maybe it's not a normal distribution. Maybe you're going to assume the population follows a chi-squared distribution and the parameter is the degrees of freedom. Or maybe you're assuming the population follows a beta distribution and you have these two shape parameters to determine that. So those are all kind of parametric assumptions, and that's why we call this parametric bootstrap. The bootstrap part comes from the phrase, pull yourself up by the bootstraps, okay? And that's kind of the idea of accomplishing something, getting your task done without additional help. It's kind of like you're on your own, you figure it out, okay? And in this case, what we're talking about is we're not going out and gathering additional data, okay? Just using kind of the data that we have, we're going to try to figure out what the sampling distribution kind of looks like, right? I was trying to look up where the phrase originated from, and there's different stories. The one I kind of like the most, and so whether this is true or not, I don't know, but it kind of just made me chuckle, is I guess there's a folk tale where the hero was walking along and he got stuck in a swamp. And so to get himself unstuck, he just grabbed his bootstraps and pulled himself out, which, completely absurd, but kind of funny. So anyway, what we're going to do with the parametric bootstrap is we're going to assume that the population follows some kind of parametric distribution. So whatever it is, the normal distribution, chi-squared distribution, beta distribution, gamma distribution, t distribution, some kind of parametric distribution, some probability distribution that you learned in one of your classes at some point, we're going to assume that it follows one of these things, okay? And oftentimes you're going to use your sample, like, for example, if you're going to assume that the population follows a normal distribution, maybe you'll use the mean of your sample to say this is the mean of the population, or your standard deviation of your sample to say this is the standard deviation of the population. So at least your parametric assumptions are somewhat based in reality, okay? And then what you're going to do is you're going to just simulate drawing a bunch of samples from whatever population you're assuming. And when you do that, you're going to calculate some sample statistic. So you're going to calculate, maybe the standard deviation of your sample or the variance of your sample or whatever statistic it is that you're looking up. And you just do this a bunch of times, okay? You do a random sample, you record a statistic. Another random sample, record a statistic. Another random sample, record a statistic. You do this a bunch of times. You keep track of every single statistic you've calculated and recorded, and that's going to kind of form your sampling distribution. And so this is an example. So we have, there's the SAT exam, and, there's the math part and then the verbal part. Technically, it's called the EBRW, the Evidence-Based Reading and Writing Exam. And they are designed to be normally distributed with a mean of 500 and a standard deviation of 100 for the population of high school seniors, okay? But it's not exactly normal because the maximum is capped at 800 and the minimum is capped at 200, okay? So, those are 3 standard deviations away, so it should cover everybody, but technically the true normal distribution goes from minus infinity to plus infinity, so it's not truly normal. It's kind of, you have these kind of forced caps there. And then, and the scores are rounded off to the nearest 10. So you can get like a 640, but it's not possible to score a 638 on the SAT, as everything's going to be a multiple of 10. And the truth is that in reality, scores are not actually normally distributed. They're designed to be normally distributed, but the population, the students who take the SAT exam is not the general population of high school seniors. It's basically only students who are expecting to go to college, which is not everybody, okay? And so your distribution ends up being a little bit skewed. But just for the sake of this example, we're gonna just go ahead and assume that it is normal with a mean of 500 and a standard deviation of 100. And we're gonna take a random sample of 15, I guess, high school senior students, random sample of 15 students. And the question is, what is the sampling distribution of the sample variance S squared, right? So if we calculate the variance of the sample, what is the distribution of, possible S squared values, right? And so there's actually a probability distribution that can be used to model the sample variance. of a sample of random normal values. And maybe you remember it, maybe you don't. If you think you remember it, you can throw it in the chat. No right, I mean, there is a right answer, but no judgment here, okay? So what's the probability distribution that we would use to model the sample variance, right? Okay, so anyway, even if you don't remember it, this is what it's gonna, how we can simulate the sampling distribution of variance. And technically, again, it's not truly normal because we're putting in these caps of 800 and 200 and things like that. Okay, so anyway, we're going to take a random sample of normal values, normally distributed values. We're going to take 15 of them where the mean is 500 and the standard deviation is 100. So that's going to be my sample. I'm going to round values to the nearest tens place. So I actually round to the -1, and that's going to round to the nearest tens. And then if any values are over 800, we're going to just cap it off at 800. If any values are under 200, we're going to cap it off at 200. Otherwise, just use the value that appears in the sample. And so this is what our sample looks like. We got 440, 520, 420, 660, 530, et cetera, et cetera. And the variance of this sample of 15 values is 10,120.95. Okay, so this is the variance of this particular sample. And so I'm going to build up a sampling distribution by just repeating this exact same thing 10,000 times. I'm going to do it a whole bunch of times. So I'm going to say, here I just create a vector to store all of my sample variances that I'm going to observe. This vector is a length 10,000. Okay. And then we're going to say for, each thing in sample variances, what we're going to do is we're going to do the same thing. We're going to take a sample of 15 values from the normal distribution. We're going to round them off to the nearest 10. We're going to kind of cap it at 800 and put a cap at 200 on the low end. And we're going to calculate the variance of whatever sample of 15 values we have. And we're going to record that variance into the vector sample variances in position I. Okay. So this loop runs and we're going to get 10,000 samples of 15. And we're going to get the variance of each of those 10,000 samples, and they're going to get stored here. And so I ask, what are some summary values of this? Okay. And so most of the time we're getting a variance of around a little under 10,000, 9,626. The mean is a little over 10,000, 10,045. One sample had a variance as low as 1,540. Okay, so that's like almost everybody got like the same score on the SAT verbal there. And here, on the upper end, our max, the largest amount of variance we observed is, close to 30,000. Okay, so quite a large variance. Okay, Q3 is around 12,000, Q1 is around 7,300, things like that. And here's just the histogram of all of the sample variances. And so we can see, the center is around 10,000, which would be 100 squared. And it's skewed right because, as far as upper ends of the variance, it can get quite high. And on the low end, it's not going to get much, well, it's impossible to have variance less than 0. So on the low end, this is kind of the low end here. And so, we have something that's skewed right. Okay. All right, so going back to the pop quiz, yes, the answer is indeed, what's the probability distribution that we would use? It's the chi-squared distribution, okay? And if you don't remember these kinds of things, that's okay. I'm not expecting you to remember this. And you can always go to Google and you can say, what is the sampling distribution of the sample variance? And, there's going to be something that pops up that says it's the chi-squared distribution, okay? And so the setup is if x1 through xn are IID drawn from the normal distribution with mean mu and variance sigma squared, and we're looking at the distribution of s squared, the sample variance, it's going to basically s squared is going to come from the chi-squared distribution. Okay, chi-squared distribution with n-1 degrees of freedom, but you do have to kind of multiply it by some constant. Okay, so you take your variances and you multiply this by this constant n-1 over sigma squared, and this statistic will come from the chi-squared distribution with n-1 degrees of freedom. And so if I take the sample variances that we sampled and I just kind of rescale it by that constant n minus 1, 15 minus 1 over s squared 100 squared, this is the distribution that we get, and I can overlay the chi-squared distribution density, and we can see there's very good alignment between the chi-squared distribution and the histogram of variances that I generated from my sample. Okay, but again, the whole point of this was that you can just use this sample variances, and this thing is supposed to be a stand-in for this red line. Okay, because if you don't remember the mathematical distribution that you should use, what we're basically saying via the bootstrap is that you can get an approximation by using, this sampling distribution that we're approximating or simulating here. Okay, and so yeah, it looks like it works out here. And so then we can do some statistical inference, right? So let's say I have a sample of 15 scores, and my sample has a variance of 20,000. Okay, my sample has a variance of 20,000. And so we ask, is it reasonable to believe that this sample is not randomly drawn from a population where the mean is 500 and standard deviation is 100? Is that a reasonable thing to believe, or is this different enough from, say, 10,000, which is what we would expect our samples to have, the variance that our samples to have? Is that different enough to kind of come to this conclusion, or is it possible that this comes from a population where the mean is 500 and standard deviation is 100? Okay, and so we can just get an empirical p-value by looking at this value 10,000 and comparing it to our sampling distribution that we simulated. So we look at this thing and we say, well, how often does just a random sample, remember all of these random samples were just generated by drawing 15 random values from a normal distribution. How often does a sample of 15 produce a variance greater than 20,000? Okay, and so that's going to be whatever this area is in the tail. How often does that happen? Okay, well, it says it happens around with a probability of 0.012. So out of 10,000 samples, maybe it happened 120 times. Okay, and so, it doesn't happen very often. Depending on what our alpha, our significance level is, we may or may not reject the null hypothesis. So if I had alpha equal to 5%, I might say this empirical p-value of, basically 1.2% is low enough for me to reject the null hypothesis. And I'm going to conclude that whatever sample I have here, my sample of 15 SAT scores, is not a random sample drawn from a population where the mean is 500 and standard deviation is 100. That it's coming from some other population, maybe a population with a greater variance or something else, or it's not a random sample. That's what we have. Okay. And again, we can do this for any kind of statistic, any kind of value that comes from a sample. And so, we were talking about the sample variance, which is, I think something that has been studied quite thoroughly. We could do it for something like the highest score in the class. Okay, so let's say we have a classroom with 25 students, and these students are a random sample. That's probably a bad assumption because schools generally don't just put students randomly together. They might separate them out based on different tracks and things like that. But what we're going to be curious is, what is the sampling distribution of the highest score in the class? Okay, so if we say, you have 25 students here, what's going to be the highest score, and what's the sampling distribution of the highest score? Okay. Or, we ask this probably, what's the probability that the highest score in the class of 25 students is 750 or higher? Okay. So there is a theoretic distribution that can be used for describing extreme values. And this is, it's known as the Gumball distribution. I don't know how many people are familiar enough to use it. And so again, we're going to just kind of get an approximate answer by using parametric bootstrap. Okay. And it just comes from the assumption that we're going to assume that the population looks a certain way. All right, so we're going to use the computer's ability to generate random samples, simulate the sampling distribution. So here, what I'm going to do is I create a vector for the highest score. We're going to take a sample of 25 values from the normal distribution where the mean is 500 and standard deviation is 100. I kind of put in the rules for this SAT scores about rounding it to the 10 and capping it at 800, 200. And then from the sample, I'm going to just take the maximum value. I'm going to take the largest value in the sample, and I'm going to record it in my vector of highest scores. And so what we see is that, you know, most of the time, the highest score in a classroom of 25 students is the highest score, something around 690. Okay. The 75th percentile is 730, you know, first quartile is 660. So generally we're getting something between 660 and 730. You know, with enough samples, we are hitting that maximum of 800. Okay. But, you know, in one instance, we had a sample of 25 students and the highest score in that sample of 25 was 540. Okay. And here is what that distribution looks like. Okay. And we see kind of a spike here at 800, and probably what the real distribution should look like is that this should probably level off a little bit more gently. But because of the rules of the SAT, where the highest score is capped off at 800, you know, we see this kind of this bump here at 800. And so, so there's actually not going to be a real true mathematical or theoretic distribution that's going to look like this. Okay. And so, you know, probably the simulated sampling distribution is the best choice to use here. Okay, so this is the distribution of the highest score in the class. And we can say, okay, well, how often is the highest score 750 or higher? So we can draw kind of a line at 750 and just say, you know, what proportion is greater than 750? So here I can just ask, you know, here's this vector is length 10,000. It's got a whole bunch of different highest scores, and we're going to say how often is this highest score greater than or equal to 750. This is a logical vector. I take the mean of it to get the proportion that was greater than or equal to 750, and it says, you know, with a sample of 25 students, this happens around 16% of the time, 0.1639 with that probability. Right. How does this feel? So far, so good? Okay, great. Thank you. Thanks for that thumbs up. Let me give you, have I given you any of your view quiz answers yet? Okay, let me go ahead and give you, I'll give you your first two. The first two are A and C. Your view quiz answers are A and C. Those are your first two view quiz answers. A as in apple, C as in cat. What if we decided to take a sample of 50 random students instead of 25? 50 random students instead of 25? Well, it's simple. I'm just taking the exact same code and I'm just changing the number of students or number of values to draw from the normal distribution to 50. Okay, we're just changing this to 50. Again, we're still recording the largest value in our sample as our highest score, and we're going to say how many times is our highest score greater than or equal to 750. Okay, and so now my probability goes up to 29%, 0.2965, around 30%. Okay, so if you have a random sample of 50 students, what's the probability that the highest score is over 750? That jumps up to around 0.2965. Okay, and so this is kind of the beauty and the power of the parametric bootstrap. Is I think the process is rather straightforward. You're just going to say, I think this is what my population looks like, and I'm going to draw random values from my population to say this is my sample, and then I'm going to calculate whatever statistic it is that I'm interested in. Okay, so I'm going to do another example here, and this one is just to kind of show you that you can do almost any statistic, really, any value you want coming from a sample. You can probably set up a little simulation here to do parametric bootstrap, right? Okay, so here my example says a high school has 200 students in its senior graduating class, and the school administration is very proud of itself because 10 of its students scored 700 or higher on the SAT verbal. Okay, And so the school administration says, oh, look, we're doing a great job preparing our students for college. Just look at these SAT scores, right? We got 10 students who scored 700 or higher. And so the question is, does this sample, does our data show evidence that our student body is something other than a random sample just drawn from the general population, right? The general population has a mean of 500 and a standard deviation of 100. Do we have evidence that our student body is something different from a sample drawn from the general population? Okay, but this is a little strange because we're looking at kind of 10 students over 700. Like, how do we figure that out? Okay, so basically we want to know the sampling distribution of the 10th highest score in a random sample of 200 scores. Okay, so we're going to look at the 10th highest score. So I'm going to create a vector called 10th highest. This is where I'm going to store the 10th highest score in a random sample. Okay, and again, I'm doing this 10,000 times. And so here my sample is going to be 200 scores from the normal distribution. I kind of implement the rules of the SAT score to, to do that. And then what I do is I'm going to take my 200 values. I'm going to sort them in decreasing order. Okay, I'm going to sort them in decreasing order. And then I'm going to take the 10th value. So that's going to be the 10th value, 10th highest value in my sample. And we're going to store the 10th highest value into this vector here. Okay, and so this will be the sampling distribution of 10th highest scores. And we want to know is if that 10th highest score, how often is that 700 or something more? So I'm going to say, all right, how often is my 10th highest greater than or equal to 700? And it happens about 3.5% of the time, 3.5% of the time. Okay, so my empirical p-values are about 3.5%. And so what that says is that if 200 scores were drawn from the normal population, it's not that likely. There's not a huge probability that the top 10 students will all have scores of 700 or higher. So maybe it's reasonable. It is reasonable to conclude that the sample of students is not randomly drawn from a population where the mean is 500 and standard deviation is 100. Okay. But again, the results, okay, these results, statistics is not able to really tell us why just yet. Okay, so we can't say whether these high scores are a result of whatever the school's efforts are. Okay, we don't know what they're doing. Okay, or if there's other circumstances surrounding the high scores, maybe there's certain things about the school. Maybe the school's located in this, I don't know, area where, I don't know, there's it attracts high performing students. Who knows? Okay, so whatever it is, this is just the results. Okay, all we're saying is that it's not super likely for this to happen randomly. Happens around 3.5% of the time. It's not impossible, but it's also not highly probable either. Okay, all right, so in summary, if you're comfortable with kind of stating that the population follows a certain parametric distribution, you can use Parametric Bootstrap to simulate the sampling distribution of any sample statistic. Okay, whether it's the highest, 10th highest, or some other number that you can think of, you can do that. Okay, and then once you have your sampling distribution, you can then use it to perform inference to calculate p-values and the like. All right, let's keep going on and take a look at non-parametric bootstrap. Okay, so when people use the term bootstrap, they're probably referring to non-parametric bootstrap. Okay, and so non-parametric bootstrap is not going to make any parametric assumptions about the distribution of the population. So, in these previous examples, we all said the population, is normally distributed with this mean and the standard deviation. Okay, and you don't always have to assume a normal distribution. You can assume the population has other shapes, like we're going to assume the population has a chi-squared distribution, or the population has a t distribution, or the population has, whatever distribution. But if you're saying the population has this distribution, that is going to be parametric bootstrap. You're making parametric assumptions about that. Okay, non-parametric bootstrap says, I'm not going to do any of that. We're not going to make any kind of parametric assumptions. Okay, the assumption you are making, okay, it's impossible to do statistics without making some assumptions. Okay, The assumption you are making in non-parametric bootstrap is that your sample has been randomly drawn from the population and is therefore representative of the population. Okay, you're gonna, all right, and so that seems reasonable that my population is representative of the population. Okay, but non-parametric bootstrap takes it a little bit farther, maybe to the point where you're not super comfortable with this, but this is kind of the next step, is that it says, well, if this is representative of the population, then what I can do is I can take my sample, and to kind of simulate the population is I'm going to take my sample, I'm going to just kind of clone it a whole bunch of times. I'm going to just make copies of my sample over and over and over again. And so now I have this big thing that looks kind of like the population. Okay. And so, so you could imagine, like, I don't know, you're filling out some picture, and it's like a picture of a stadium, and you need to fill up the stadium so it looks like it's full of people. And so, so what you can do is maybe you have a picture of a small crowd of like 30 people, and you're going to just basically use copy and paste, and you're going to just copy and paste that group of 30 people, or maybe like 100 people, and you're going to just copy and paste it all over the entire stadium, so that now you have this huge group of people, okay, or quote, group of people that is supposed to stand in for the population. Okay, so it's kind of like using that cloning tool in Photoshop to kind of just duplicate things. Now, if there's something unusual in your sample, like there's a person who's really tall or something a little bit strange in your sample, that's going to get duplicated throughout. And, you know, obviously it's going to kind of skew your results of what the population looks like. But the hope is that your sample looks kind of like the population, and therefore cloning it and duplicating it many times to create this fake version of the population is like a reasonable thing to do. Okay. And so, you know, I don't know how you feel about that, but that's basically the premise of the non-parametric bootstrap. Okay. A question in the chat says, does this mean we will never use our norm in non-parametric bootstrap? And that is correct. In non-parametric bootstrap, you will not use things like R norm or some other, you know, random beta or whatever, you know, whatever distribution. You're not going to be using stuff like that. We're going to be doing sampling with replacement. Okay. So you don't actually, so from a computational standpoint, you don't actually have to take the sample and duplicate it like millions of times to create your big population. You don't actually have to do that. You can get the equivalent by just taking your sample and sampling it with replacement. Okay, taking your sample and sampling with replacement is mathematically equivalent of taking your sample and duplicating it like a million times, or technically an infinite number of times. So you don't actually have to duplicate it. You can just take your sample and sample with replacement, and that's effectively taking your sample and cloning it a whole bunch of times to make your fake giant population. Okay, and that's what we're going to do to create our sampling distributions. So just to kind of recap a few of these methods that we've discussed so far, is that if the data you have was obtained via random sampling, you can use non-parametric bootstrap. Okay. If the data you have was obtained via random sampling from the population, and you're willing to make basically distributional assumptions about the population, you can use parametric bootstrap. So if you're willing to say the population is normal, or if the population has this distributional shape, you can use parametric bootstrap. On Monday, we talked about the randomization test. And the key difference there is that if the data came from an experiment where random assignment was used, you'd use the randomization test. Okay. And so the key difference between Monday's example and today's example with non-parametric bootstrap is the work is going to look similar, but one is basically sampling with replacement and one is without replacement. And the key assumption is that for the randomization test, the assumption of exchangeability is true, that any arrangement of people and basically treatments is equally valid. Whereas that's not going to be the case when you have a random sample from an observational study. Okay. And here I wrote both, but in all of these cases, we're going to create a sampling distribution by simulating a bunch of instances where the sole source of variation is just random chance in our sample. Okay. All right. And so the example that we're going to take a look look at comes from this textbook, Ziefler, which I've linked in the homework, and you should all have free access to it as long as you're connected via the VPN, okay? All right, so this I just copied straight from the textbook. And it says the Center for Immigration Studies at the US Census Bureau reported that despite shifts in the ethnic makeup of the immigrant population, Latin America and Mexico specifically remains the country's greatest source of immigrants, okay? Although the average immigrant is approximately 40 years old, large numbers of children who enroll in US school, large numbers are children who enroll in US schools upon arrival. Their subsequent educational achievement affects not only their own economic prospects, but also those of their families, communities, and the nation as a whole. So Stamps and Bowen, which are the researchers, studied the educational achievement of Latino immigrants by examining a random sample of 2,000 decennial census data. So this is from the 2000 census, which is already 20 years ago. And it's in this file, latinoed.csv, okay? So one interesting research question that emerged from the research is whether there is a link between where the immigrant originated and their subsequent educational achievement. Specifically, the question is if there's a difference in the educational achievement of immigrants who came from Mexico and immigrants who came from other Latin American countries, okay? So this is going to be the thing that we're looking at. And so we have 150 immigrants living in Los Angeles. That's going to be the our data set that we're looking at, okay? And specifically, we're looking at Latino or Latinx immigrants in LA. And we're going to look, the variable that we're looking at is this educational achievement level. And I tried to figure out what these numbers mean, but I couldn't figure it out, okay? So the numbers range from 1 to 100, and I'm not quite sure. It says higher values indicate higher levels of educational achievement, but I don't actually know what they mean. Because a lot of times education values are measured in like years of formal schooling. So if you graduate high school, it's like you have 12 years of formal schooling, and so your education number is 12. If you graduate college, it's like 16 years of formal schooling. And, you know, if you graduate some other thing, you get some other number here. But I don't know what 1 through 100 means. It's not going to be years of schooling because nobody has 100 years of formal education here. So, so I don't know. We're just going to have to go off of the numbers that they've provided. Okay. They have other information here, but really the variable that we're going to look at here is going to be whether the immigrant came from Mexico or a different country, okay? If they came from Mexico, this value is going to be a 1. If they didn't come from Mexico, they came from another Latin American country, it's going to be a 0. Okay, and so this is kind of just a sample of first few rows of our data set. And so we're going to look at this number, you know, achieve 59.2, 63.7, 62.4. And again, I don't know exactly what these numbers mean. And then we're going to look at this column for whether the person came from Mexico or somewhere else. Okay, and so just to kind of do a quick summary analysis, you know, I just said group by the variable, whether they came from Mexico or not. And then we're going to, you know, I did a count. There were 34 people who did not come from Mexico, 116 people who did come from Mexico. And then I said, you know, give me the mean of achieve. And then so the mean value for education achievement for people who did not come from Mexico is like 64.5. For those who did come from Mexico, the mean is 58.6. And if we take the difference between 58.6 and 64.5, and this is actually just rounded off, you know, that difference is negative 5.92. Okay, for two groups of that we're studying here. All right, and so just kind of a little bit more on exploratory analysis. Here's a side-by-side box plot. Okay, we're just kind of comparing, you know, is there a difference in the median scores or things like that? We're actually looking at the mean. Okay, and here's a density plot. So I've got kind of two density curves overlaid on top of each other. And they're similar, but a little bit different. And it's hard to really make judgments here about whether the difference that we're seeing between the two groups if that is statistically significant or not, okay? And so right now we're, you know, if we did a traditional analysis like a t-test, okay, and maybe we're allowed to do a t-test because, you know, our sample sizes are large, so maybe the central limit theorem will apply, okay? So maybe it's okay, or maybe we shouldn't. But so if we did a traditional t-test, you know, our null hypothesis would be kind of like the mean education achievement level for immigrants from Mexico minus the mean education achievement from immigrants from other countries, that there's no difference between them. If we take the difference between these mean values, we're going to get 0. And the alternative is we're going to get some non-zero difference between these two mean values, okay? And so if you do the t-test, we get a p-value just under 5%, okay? So, you know, maybe it's significant, but just barely at the 5% level, okay? And so, you know, maybe you would reject the null, or maybe you wouldn't, depending on what you use for your significance level alpha, okay? So we get a p-value of around 0.04597, 0.04046, something around there. We can do non-parametric bootstrap, okay? So for non-parametric bootstrap, what we're going to do is we're going to assume that our original sample, and remember in our original sample, we have 150 people, 116 who came from Mexico, 34 who came from other countries. We have 150 people. We're going to assume that that sample is representative of our population. And so what we're going to do is we're going to just resample that with replacement. And that's effectively taking my 150 people, cloning it a bunch of times, and I'm saying this represents the general population of all immigrants from Latin American countries, okay? And whether that's a safe assumption or not a safe assumption, you know, that depends heavily on, you know, how accurate or how good our sampling process was in the beginning, okay? My null hypothesis is still going to be kind of the same, okay? That there's no difference between the mean education achievement level for both groups. And basically, if we're assuming that the variances are equal, then this null hypothesis is effectively saying that the values that we've observed in our sample come from the same population, okay? If the null hypothesis were true, the values are basically coming from the same population, the same mean, same variance type of thing, okay? So, sorry, this should say non-parametric bootstrap, that's a typo, okay? If the null hypothesis were true, the achievement scores for Mexican immigrants come from the same population as the achievement scores for other Latin American immigrants. With the parametric bootstrap, a non-parametric bootstrap, we're going to assume that our sample of 150 observed achievement scores is representative of the entire population. And to simulate our sampling distribution, we're going to draw two random samples, one of size 116, the other of size 34, by resampling the 150 scores with replacement. Okay, and we're going to do this over and over again. Each time we're going to calculate the difference between the group means. Okay, and we're going to do this a bunch of times. So this is what my sample code looks like. Okay, I have a vector of differences of length 10,000, and I'm going to iterate this 10,000 times. Each time I'm going to take, I have group A. This is going to be 116 values drawn from the entire population of 150 values, right? So I have 150 values. I'm going to draw 116 of them with replacement. So I'm assuming that my entire sample of 150 is representative of the population. And if the null hypothesis were true, both samples are coming from the same population, okay? And what we want to know is like, how often do we get just different values or different means from just two samples coming from the same population? So I'm going to have one sample of 116, another sample of size 34. Both are just drawn with replacement from the same population of 150 values, okay? We're going to take the mean of group A, subtract off the mean of group B, and store that in the differences, okay? And I do that 10,000 times, and what we want to know is how often do we get a difference of basically 5.9 or something more extreme. Now, the observed difference I recorded was negative 5.9. And so if I do the absolute values, the 100% of the absolute values are going to be greater than negative 5.9. So we don't want to do we don't want to do this. What we're going to have to do is we're going to have to do the absolute value of the differences compared to the absolute value of the observed difference. And it happens, we get a p-value, empirical p-value of, again, just under 5%, around 4.6%. So this aligns quite closely with our t-test, okay? And so it shows that, you know, when we draw random samples from the same population, sometimes we get mean differences of 5.9 points from just random chance alone. This happens a little bit less than 5% of the time. So, you know, depending on the significance level that we're using, we might reject the null hypothesis and we might say that, you know, according to this data, there seems to be a difference between the mean education achievement of, you know, the two different groups of people. But, you know, maybe that difference isn't that significant. I mean, it's barely significant at the 5% level. So maybe we would opt to be a little bit more cautious and not reject the null. And we can't really make any kind of cause and effect conclusions. Okay, the split, the reason why I have 116 here and 34 here is because I'm trying to match the size of my two samples when I summarized my data. Okay, so when I summarized my data, I had 116 people in the kind of the observed data that I have 150 people total. 116 of them came from Mexico. 34 of them came from other Latin American countries. So that's why I had the split for 116 and 34. So I'm asking how often will just random samples produce a difference like this, because that's what I have for these two random samples here, or not, I guess, yeah, random samples in our observed data. And we're just saying, if we assume these are coming from the thing, we're going to draw two random samples, one of size 116 and the other size 34. Okay, so that's going to be our empirical p-value. I'm going to run out of time, so I'm not even going to bother covering this, but basically I can do approach this from a parametric bootstrap, okay? And if I do it from a parametric bootstrap, again, we're going to say under the null hypothesis, both sets of values come from the same population. And so when I run my code, we're going to just take the mean of all 150 values. We're going to take the standard deviation of all 150 values. And then I'm going to generate, using the normal distribution, 116 values from this normal distribution where the mean is the mean of everybody and the standard deviation is the standard deviation of everybody. And then I'm going to draw another sample of 34 values from the exact same population where the mean is the mean of everyone and the standard deviation is the standard deviation of everyone. Okay, so here under the parametric bootstrap, we're assuming that the entire population is going to have this mean and this standard deviation based on the data that we have. And the null hypothesis basically says group A and group B are both coming from the same population. And we want to know, if the data do come from the same population, how often do we get differences that are as big as the difference that we observed, our observed difference. Okay. So I'll let you read through these slides a little bit more more closely. Okay. Yes, I will upload the data to CCLE. I think for the homework you have, it references data as well, and you can access those from GitHub. So I'll link to kind of the GitHub data on CCLE. So if you wanted to kind of run the code yourself on this data set, you can. Okay, let me give you your last view quiz answer for today. Last view quiz answer is E. E as in elephant. E as in elephant is the last view quiz answer. All right, so we'll end here for today, and we'll see you guys on Friday. And so have a good night, and we'll see you then.